Greetings, AP Chemistry. This is Mr. Harper, and this podcast is part one of a Chapter 14 overview. You don't have to watch this. This is not required, but consider it supplemental. If you want to go back and review Chapter 14, I'm going to podcast here what we did in class mostly. So today we're going to talk about is solution formation and the way that happens and some solubility stuff. And then in the next one I'm going to make, we're going to talk about the colligative properties and how to use those. You may find this helpful maybe for review prior to the AP exam. So here we go. Let's talk about the solution process and how solutions form. Now, the question you may have in your mind, or that you may have had before we studied Chapter 14, is, well, why is it that solutions form? And the answer to the question, why does anything happen in chemistry, is because at the end of the day, it's energetically favorable. If we think about the solution process, okay, that can be explained using this diagram right here, like we saw in class. So we're going to start. A solution is always two parts. We have a solute, okay, and we have a solvent, okay. Now, let's consider for the sake of example that our solute is sodium chloride, okay, and our solvent is water. In order for a solution to form, these two things right here have to mix. But for that to happen, what must first happen is we have to go through a couple steps. We can think about the process as being multiple steps. The first step is expansion of the solute, we call it. So our solute here, which is sodium chloride, originally in a crystalline form where our particles are very closely packed together, has to be separated and expanded. So those ions have to be separated and from each other. In order for that to happen, we have to destroy or overcome the forces of attraction that are acting between the ions here. So if you imagine this is a sodium ion and this is a chloride ion and this is a sodium ion, whatever, what we have to really do here is disrupt the ionic bonds. So step one is we're going to disrupt the ionic bonds between the ions, and this step has a certain delta H or energy change associated with it. Because we are disrupting ionic bonds, we know that this step is going to be endothermic. Or in other words, it's going to require energy, and delta H is going to be positive and it is going to be large because that takes a lot of energy in order to separate the solute particles from each other. In a similar fashion, in order to create our solution, which is pictured down here, we have to first separate the solvent molecules from each other. So here we have water molecules. Now, of course, we know, guys, we have water molecules that are in the bulk substance. These molecules will be attracted to each other by hydrogen bonding, okay? So step two, we have to expand the solvent, and in order to do that, we have to disrupt hydrogen bonds between the water molecules. Again, this step, delta H2, because we are breaking the intermolecular force of attraction here between the solvent molecules, this is going to be positive, and it's also going to be relatively large because we know that hydrogen bonding is a relatively strong intermolecular force of attraction. So here we have the expanded solvent. Now the last step is we take our expanded solvent and we take our expanded solute over here and we mix those. So here we have the mixed solution right here. Now when we mix the solute and the solvent, new attractions can form between solvent and solute particles. Okay, now when those new attractions form, in this case we're looking at sodium chloride, or rather we have sodium ions and we have water molecules. When these get near each other, these can experience for each other ion dipole type attraction. Now, of course, we know that those are relatively strong attractions. So we have these new attractions that form. That is energy releasing. So this last step, all the time, in any case, when we're forming a solution, this is going to be an exothermic process. Delta H3 here is negative, and this is also going to be large, okay? Now, the overall delta H for this entire process, we think about this, we broke it down into three steps. Step one, step two, and step three is the mixing. The overall heat change for the solution process is going to be the sum of delta H1 plus delta H2 plus delta H3, okay? And this is kind of like another statement of Hess's law almost, because in Hess's, when we used Hess's law back in chapter 6, we broke a chemical reaction down into steps, and then we saw that the overall delta H of the whole process is the sum of delta H of each of the constituent steps. Well, this is the same basic idea. Now, when we take the sum of each of these steps, the heat of the solution, in order for a solution to form, must be either negative, okay, meaning overall the process is exothermic and is going to be energetically favorable, or delta H can also be small and positive. So it can be positive and it can be small. If delta H is positive and it is small, then it does still require energy to get the solution to form, but there's sufficient energy for just from thermal the surroundings in the classroom or wherever to get that to happen. So these are the conditions under which, energetically speaking, a solution is going to form, and that explains why it is that ionic compounds usually will dissolve, or often, I shouldn't say usually, but often will dissolve in water. It's because overall, if we look here at delta H3, more energy is released when the solution forms than it requires to separate or expand the solute and to expand the solvent, respectively. So there we go. And we just talked about that. So never mind. So this is just what we just talked about in words. So in order for the solution to form, delta H has to be either negative or small and positive. And that's why we have these rules of thumb. We know that like substances will dissolve other like substances. And the reason for that all goes back to this delta H idea. Polar things tend to dissolve polar substances. So we have a polar solute that will tend to dissolve a polar solute. And the reason why is because if we have a polar solute and a polar solvent, there's strong attraction possible between solvent and solute particles. Okay? Also, we know that nonpolar things tend to dissolve nonpolar, okay, solutes. Now, an example of this would be something like if we had, let's think here. How about, we'll say hexane, and we dissolve benzene in it. These are both two non-polar substances. These will dissolve in each other. Now, again, this goes back to the whole idea of the delta H for the solution formation. If we consider, okay, we'll go back. Let's just go back to the diagram here really fast. If we consider here, I'll erase some stuff here off my diagram. If we consider this diagram, now we change the identity of our solute and our solvent. So instead of having our solute be sodium chloride, let's make this hexane. Okay, hexane is a non-polar organic solvent, and we'll call this maybe. Okay, sorry, put in the wrong spot here. So we'll call this again benzene. Benzene is a non-polar organic solute. Again, in order for a solution to form, we have to separate or expand the solute particles. To do that is going to require energy. Delta H is going to be positive, but if we consider the type of attraction that can occur between benzene molecules, these are nonpolar, so the only possible attraction or type of attraction between benzene particles is weak London dispersion forces. Because the attractive force between benzene molecules is weak, it does not take a lot of energy to expand the solute. So delta H here is positive, but it's positive and it is small. Now, if we were going to try to dissolve benzene here in water, okay, let's consider the case with water. We said before with water, if water is our solvent, if we try to expand the solvent here, it's going to require energy to break the hydrogen bonding that's happening between water molecules, and that delta H is positive and it is large. If we look at what happens here when we try to mix the solute and the solvent, you just erase all this stuff here, okay? We think about the type of, okay, we'll go back. Okay, we know water here is polar, and benzene is not. Benzene is nonpolar. So when we mix the solute and the solvent particles, new attractions are going to form, but the only type of attraction that's possible between benzene, which is nonpolar, and water is going to be London dispersion forces. Therefore, delta H3 is going to be negative, but it's going to be negative and it's going to be small. So if we look at the overall process, the overall heat of the solution, if we're using water as our solvent and benzene as our solute, okay, delta H1, this term here is small, okay, delta H2, this term here is going to be large, and it is positive, Okay, and delta H3, this is going to be negative and is going to be small. So if we look here at the overall process, okay, the sum of, for this process of delta H2, delta H3, and or delta H1, delta H2, delta H3, overall the heat of solution is going to be positive. It's going to be large because the dominant factor here is the amount of energy that it takes to expand the solute. When we mix, okay, we go down here to the third step, delta H3. When we mix our solute and our solvent, there's only a little bit of energy here that is released. So overall, delta H for the overall process is going to be large and positive, and this is non-favorable. This is why non-polar things like benzene or like cooking oil do not dissolve in water. It all goes back to energy. It is energetically unfavorable. It requires a lot of energy to get these things to mix, and that is why this does not happen on its own. You can force it to happen by adding energy into the system and by mechanical mixing and things of that nature, but it doesn't happen by itself. Now, let's change this picture again a little bit here. Let's change the identity here of our solute and, or not our solute, our solvent rather, and let's make this, we'll go back here. Let's make this hexane. If we change our solvent to hexane, hexane is a nonpolar solvent, benzene is a nonpolar solute. To expand the solute, or the solvent, again, rather, requires energy. This is still an endothermic process, but to expand hexane, the only type of attractive force possible between hexane molecules is London dispersion force. This is relatively weak, and so delta H for this step 2 right here is going to be positive, but it's going to be positive and it's going to be small, okay? Now, because it does not take a lot of energy to expand the solvent or to expand the solute, okay, these terms, delta H1 and delta H2, are both going to be positive, but they will be small, okay? Instead of being large, they're going to be small. And delta H3 here is going to be small, but overall, the entire process, delta H, the heat of solution, if we take the sum of each of these steps, is going to be negative and it will be small. So overall, for mixing a nonpolar solvent and a nonpolar solute, delta H is going to be negative, which means the process is favorable, and that's why nonpolar things mix. So again, guys, when we try to predict if a solution is going to form, we have to think about the types of attractive forces that are possible between the solvent and the solute particles, and what the energy change for these different processes is going to be. Okay. And that's what we said, polar, so just kind of going back here to our rules of thumb, we know that like dissolves like. The thing you want to remember, and this is all going back to delta H. We know that polar things will dissolve, polar solvents will dissolve a polar solute, non-polar solvents will dissolve a non-polar solute, and a polar solvent will not dissolve a non-polar solute. Okay, again, for the same reasons we were talking about here just now with delta H. Okay. Okay, we'll skip that. Let's talk about solubility now for a while. So we've talked about how solutions form and why they form in terms of delta H. We're going to connect this here to some ideas about solubility that you have learned before. Now let's look at what this word solubility means. Solubility refers to whether something will dissolve. This is true, but it also is a quantity. The solubility of a substance is the quantity that will dissolve in a certain amount of the solvent. Now, if we're looking at aqueous solutions, usually this is going to be listed as a quantity. If I ask you, what is the solubility of potassium nitrate at 50 degrees Celsius? Well, what you're going to give me is a number, and it looks like this. It's going to have the grams of your solute per 100 grams of the solvent, which in this case is usually going to be water because we're dealing mostly with aqueous solutions. Now, this right here is called the solubility curve, this graph. And what it shows you is a solubility on the y-axis of different compounds as a function of the temperature, okay? Now, for most solids, okay, we see that the solubility of most solids increases as the temperature increases, okay? And there's a reason for that. Okay, so we look, for example, at potassium nitrate and sodium bromide and sugar. For each of these solutes, we see that the solubility curve has an upward slope, and the solubility goes up as we increase the temperature. Now, let's think about why that is. Okay, if we consider potassium nitrate, if we think about what happens when potassium nitrate dissolves, okay? Potassium nitrate, if we take this as a solid and we put this in water, And when that dissolves, it dissociates. It's going to split up into its constituent ions. So we're going to get a potassium ion, which is going to be aqueous, plus a nitrate ion, okay, out, which is also going to be aqueous, okay? Now, in any chemical process, guys, we can think about heat as being either a product or a reactant of the process. Now, in this case, guys, as we add heat, okay, to the system, we can see, if we just look here at the curve for potassium nitrate, as we add heat, we can see we're making more potassium nitrate dissolve, or in other words, we're getting more of the products over here. Now, what that means here is that heat is a reactant in this process. Heat here is required to get potassium nitrate to dissolve. What that tells us about this process, this is very important, is that this overall process is endothermic. Okay? As we add heat to the system, as we add heat, which is a reactant over here, we get more products. So we can tell the system that this is an endothermic process. Or in other words, for potassium nitrate dissolving, delta H, like we talked about before, is actually positive. But it's positive and it is small. It does not require a lot of heat to get potassium nitrate to dissolve, and that's why it will do so under normal conditions. Okay? So there we go. So anything, guys, where we see that the solubility increases as the temperature goes up, we know the delta H, we know that it's going to be an endothermic process, and that the delta H for that dissolution is going to be positive. If we consider something else, an opposite example, like sodium sulfate, for example. Sodium sulfate, we can see, okay, this is a solid. If we dissolve this in water, we're going to get 2 sodium ions and a sulfate ion, SO4 2-. And we can see, guys, that the reverse here is true for sodium sulfate. As we increase the temperature on the sodium sulfate, it becomes less soluble. What that tells us is that heat is a product, or in other words, for this process, delta H is going to be negative, and the process is exothermic. That's what we can tell from our solubility curve. Okay? So we can see for most solids, though, most solids dissolution is endothermic. Now, these two things we just looked at right here, potassium nitrate and sodium sulfate, these are ionic compounds. We know they are ionic compounds, guys, because we see a metal and nonmetal. Anytime you see a metal and nonmetal in a compound, it's always going to be an ionic compound, and when those dissolve in water, to the extent that they dissolve, they will dissociate into ions. I'd like to contrast this behavior with molecular solids. A molecular solid is one which is held together by covalent bonds. So, for example, something like sugar. If we consider solid sugar, C12, H22, O11, if we take this as a solid and we try to dissolve this in water, when this dissolves, all that happens is that it goes from a solid state into an aqueous state. If we think about what actually happens, it may be helpful for you guys to go back and look at that picture that we had up here just a second ago. The solid sugar gets expanded. So the sugar molecules get separated from each other and they get mixed in homogeneously amongst water molecules. But notice, guys, things like sugar or any other covalently bonded compound, okay, we call these molecular solids, okay, because they consist of molecules. These do not dissociate, okay? This is extremely, extremely, extremely important, okay? I'm off the screen here, but they do not dissociate. You want to write that down. They do not split up into ions. So the most common mistake I saw people make last year, we were talking about or describing dissolution of different things. They'd say, okay, our sugar here, when this dissolves in water, we're going to get 12 carbon 4+ ions and 22 H+ ions and 11 O2- ions, and that is 100% incorrect. That does not happen. When molecular compounds dissolve, they do not dissociate ever. So just carry that with you, guys. These remain molecules. They just split up and are distributed homogeneously amongst the water molecules in the solvent. Okay. Let's contrast this with the behavior of gases. We've shown how solids behave. Let's look at how gases behave. If we look at a solubility curve for gases, here we have a couple gases here: methane, oxygen, carbon monoxide, nitrogen, helium. Now, what we can see is happening here, guys, as we and the solubility is given here on the y-axis, and here's the temperature. As we increase the temperature, guys, we can see that for any gas, this solubility curve has a downward slope, meaning that always, the solubility decreases all the time as the temperature increases. A gas always becomes less soluble as the temperature goes up. Now, let's think about what this tells us, guys. What does it tell us about the thermodynamics of a gas dissolution? What this says is because all of these become less soluble as the temperature goes up, that means that delta H for any of these is going to be negative. Delta H is negative, delta H is negative all the time, all the time, all the time. It is always exothermic. Okay, one more factor that is going to be important for you to know is the effect that pressure has on the solubility of a gas. So what I have here is some pictures, and what these are displaying is something called a piston. Okay, so we have this plunger thingy right here, and what we're doing is we're applying pressure to the system. Okay, now what this is showing us here is we have, as the diagram shows, we have a solution right here, and we're going to consider what happens here. Originally, if we consider the solution, we have some molecules here that are dissolved in some solute. Doesn't matter what it is, some gaseous solute that's dissolved here in the aqueous solution. And we know that if we let this sit for long enough, what's going to happen is that we're going to at any instant have some gas molecules which are going to be coming out of the solution, again, and re-entering into the gas phase. And we're going to have some of these gaseous molecules which are going to be dissolving back into the solution and entering into the aqueous phase. If we let the system sit for a while, eventually these rates are going to become equal, and that state where the rates of the gas molecules coming out of the liquid and going down into the liquid are equal, that state is called equilibrium. Now, what's going to happen here if we apply pressure to the system? If we apply pressure, what that's going to do is that's going to force more gas molecules down here into the solution. And in other words, it's going to increase the concentration. If we think about this, once this reestablishes equilibrium over here, here's our new equilibrium. If we look at the picture, we can see that there are more gas particles now dissolved in the solution than there were here to begin with. Okay, what has happened here? If we apply pressure to the system, okay, the solubility of the gas goes up. Okay, and this is described mathematically by a relationship called Henry's law, and it looks like this. The solubility of a gas is equal to some constant, which is characteristic of that particular system, times the pressure, the pressure, okay? This is actually how soda is bottled, guys. Let's think about soda. I'm going to draw a picture of a soda bottle. At least I'm going to try. Okay. If we think about soda, soda is this is a really lame soda bottle, but soda is an aqueous solution. And there are several solutes, like sugar and that sort of thing, but the part that makes it fizzy is that there is carbon dioxide there dissolved in the soda. That's what makes it fizzy. The way that they get the carbon dioxide to dissolve in the solution is when they're bottling the soda, they bottle it under an extremely high pressure of carbon dioxide. They have these machines that pump a bunch of carbon dioxide into the bottle, and it's bottled under very, very, very high pressure of carbon dioxide. I forget how many atmospheres of pressure, but it's something like 10 atmospheres or, at least of carbon dioxide. Okay? When they increase the pressure of carbon dioxide in the bottle, what that does is it causes more carbon dioxide here too. It basically forces carbon dioxide into the solution and increases the solubility of it. And then they put the cap on, and that's how it gets carbonated. Now, when you get your soda home and you open the bottle, there's always this tss sound. What you're doing in that case is you are releasing the pressure that is on the gas. And when the soda foams, what's actually happening is since you've released the pressure that is on the gas, well, now the gas comes back out of the solution. So when you release the pressure, or when you reduce the pressure, you're lowering the solubility effectively of the gas when it comes out of the solution. So there you go, guys, an application to real life. Okay, that is the end of our first podcast out of chapter 14, just an overview. So hope you guys are having a good break, and I'll see you when we get back to school. Goodbye.